Hello and welcome to another episode of the EnVisioneering Exchange, the podcast where industry leaders discuss the most important topics in HVACR. I'm your host, John Sheff, Danfoss's Director of Public and Industry Affairs, and you can subscribe to our show on Apple Podcasts, Spotify, SoundCloud, or wherever it is you get your podcasts. Today's topic is district energy, and I am thrilled to be joined by my guest, Jeff Flannery, Danfoss's lead business development manager for district energy in North America. Jeff, why don't you tell us a little bit about yourself?
Well, hello, and thanks for inviting me, John. Again, my name is Jeff Flannery. I operate as the business development manager in North America for Danfoss with a focus on the district energy topic. And also at times getting involved in the commercial controls business, so the actuator and valve business at Danfoss as well.
Very cool. And Jeff and I have worked together on a number of instances in district energy and some other heating products. So we know each other, and I'm really excited to talk about this subject. District energy is not a well-known technology here in North America. Danfoss specializes it in Europe, so it's a really interesting topic. And when we did our press breakfast at this year's AHR show, we had a number of speakers on district energy, and most of the questions we got after the show were on this topic. So I think it's a great idea to kind of dive in and do a little digging on it and really help our listeners understand. So let's start at a real high level. Jeff, generally, what is district energy and how do you describe it?
Yeah, John, this is really a great question, and it surprises me how often it still gets asked. But Danfoss, we've been working to change that whole dynamic for more than 40 years. District energy refers to the heating or cooling systems for multiple buildings that have an interconnected system of insulated pipes for delivery of thermal energy. The thermal energy is generated typically off the immediate site at a nearby central plant and then distributed to the connected buildings via steam or hot and chilled water through the insulated pipe network. Within each building, the energy gets transferred to the building's heating or cooling system by something we refer to as an energy transfer station, which includes a heat exchanger. The energy transfer station isolates the district heating system fluids from the building heating systems and regulates the temperature on both sides of the heat exchanger. So, quick and dirty description of something that's actually quite large and complex.
I think that's what we do on this podcast, so I think it's a good place to start. And, I love this idea of efficiency in this manner and talking about a network of buildings, because I think in North America, particularly in the U.S., when we think about energy efficiency and building efficiency, we're thinking about a building as a discrete system in and of itself. But here in Europe and some other places where district energy is more popular, we're really looking beyond that discrete building and looking at a network and a system and trying to make that system as efficient as possible, where the building is just one node, right?
Yeah, exactly. And this is really another great question to follow up. So district energy systems are generally much larger than heating and cooling systems in any single building. And by combining the heating and cooling loads of multiple buildings, the district energy system operator has a lot of opportunities opening up to them that are not available to an individual building operator. And these include pretty substantial opportunities to save energy and improve efficiency of a larger system. For instance, heating and cooling equipment is operating most efficiently in a pretty narrow range of operating conditions. During shoulder seasons like early spring and late fall, when individual buildings are operating in partial load conditions, any individual building operator has to run his building in those conditions, and that forces him to run his equipment in a condition that doesn't optimize its efficiency. But a district energy operator who has a conglomeration of buildings that he's servicing can combine a whole bunch of partial loads and maximize the efficiency of a single piece of equipment by serving multiple buildings with that single piece of equipment. But even more importantly, district energy systems can benefit from an economy of scale that's simply out of the reach of most individual building systems. So exciting opportunities like the integration of combined heat and power, waste to energy topics, biomass, geothermal, lake or ocean cooling, all this becomes economically feasible, enabling much higher overall system efficiency. And these things are just not available to a single building owner.
Yeah, I mean, I think that we kind of miss the picture here in this country when we're talking about energy efficiency by not exploring how these district energy systems work. And I think we're getting a little bit more into that with the idea of microgrids, but we're still pretty far behind where Europe is and where Danfoss has a lot of experience. So let's take a step back and talk about how district energy has really developed in Europe and what that looks like now.
Well, this is something that I had to learn myself beginning about 4 years ago, because even with my experience in the HVAC industry in North America, district energy was a little bit of a new topic to me 4 years ago. But it's really tied to the global trends of urbanization. And according to the United Nations projections, an urban transition process that really reinitiated in the 1950s is still continuing today. We had an earlier urbanization process that you can associate with the Industrial Revolution in Europe, but it has intensified once again since the 1950s. In response, urban centers have had to address their environmental and energy supply challenges. And Euro Heat and Power, one of the leading advocacy groups in Europe, reported in 2017 that district heating networks in Europe are now supplying 11 to 12% of the total building heat demand in the European continent. So it's become a very big business and a very important part of the energy infrastructure in Europe. Traditional district heating systems consist of centralized power stations producing steam or extremely hot water that might even be under pressure to avoid it flashing into steam for distribution through buried pipe networks in urban areas. These high temperature first generation systems suffer from high thermal losses in their distribution systems. So for this reason, the trend has been away from steam and towards distribution of progressively lower temperature hot water. As the water distribution temperatures have gone down, it's becoming increasingly possible to integrate additional sources of thermal energy, which could be geothermal, waste heat recovery from other industrial processes. Higher system efficiencies are evolving with each new generation of the district heating system, and it's enabled by these lower temperature distribution water temperatures. It's generally accepted that the European experience has included now 5 distinct generations of district heating systems. Really, it's the 4th generation that is getting all the attention. But the 5th generation system allows you to do district heating and district cooling simultaneously, whereas a 4th generation system is more characterized by its extremely low distribution temperature and its ability to integrate diverse heat sources, something we refer to as fuel flexibility. So, it's been a long road, but we're really talking about 4th and 5th generation technology now in the European experience.
Yeah, so there's a lot there to unpack and a couple things I want to hit on. So first of all, you talk about some of these 5th generations and district heating and cooling. We'll touch on cooling in a second, but the ability to use other sources of energy and lower temperatures allows you to do some really cool stuff. And I know Danfoss has been involved in some of these projects where we're taking waste heat from a grocery store and putting it back into the network and really just making all those nodes on the grid where they used to be just endpoints, they're really turning into more generation points too and reutilizing a lot of that energy. So I think that's pretty cool. And then, like I said, I think most people think of district energy, they immediately think of district heating, but we call it district energy because it includes cooling too, right?
Yeah, that's exactly right. And district cooling is growing and growing internationally. The International District Energy Association, where Danfoss participates, exposes us to a lot of district cooling topics, not only in North America, but worldwide. And I find it really interesting to note that on a worldwide basis, more building square footage is being connected to district cooling utilities than district heating in recent years. And much of this district cooling growth has been in the Middle East. In there, building cooling can be as critical to occupant comfort as heating is here in North America. So in North America, we're also operating district cooling utilities. They exist on college campuses, regional health centers, sometimes in municipal installations all across the lower 48 states and Canada. District cooling operates just like district heating, except we're distributing chilled water instead of warm or hot water. The energy transfer station heat exchanging equipment is just working with different ranges of temperature. So Danfoss here in North America provides solutions to both the cooling side and the heating side equation.
Yeah, very cool. And I think the technology is evolving rapidly, and we're going to see more of this in the future. So speaking of that, we talked about Europe. We said that they're really on their fourth and fifth generation of technology now. What does district energy in the U.S. look like? I know we've just completed, or in the stages of completing one of our first big projects here, and the industry is on the upwith. But where are we from a technology standpoint, from a development standpoint, and where are you seeing these projects?
Well, district energy has been in use for many, many decades here in North America. There are systems in operation in North America that have been in place for approaching 100 years. So some are really quite old. It's a healthy and growing district energy market here in the U.S. We have strong industry trade associations and a cooperative network of suppliers advancing district energy. At Danfoss, we're pretty proud of our peer associations within that industry. One of the most interesting developments is opportunities being seized to convert existing steam-based systems to hot water distribution systems. And this is where the North American experience is looking to the recent, past 2 decades of experience in the European marketplace to, you might say, leapfrog those second and third generation solutions to go straight to a fourth generation system. System developers and operators in the U.S. are adopting this trend towards lower temperature hot water distribution systems pioneered by our European colleagues. And it's about enabling the fuel flexibility, which can drive efficiency and green initiatives. Danfoss is an integral partner for these low temperature hot water distribution systems around the world, as well as here in the U.S.
Yeah, and I think that's a really key point. We'll kind of get back to that steam versus hot water, but I think that most people don't realize that there are a lot of these district energy systems that have been around in old U.S. cities for a long time. New York, Chicago, those are big steam cities. And as we kind of move forward, especially with those cities looking to reduce their greenhouse gas emissions and their reliance on fossil fuels, I think you could see some of this fuel switching going into low temp hot water. But we'll get into that in a little while. Let's talk about what types of commercial buildings are best suited for district energy and where we might see this in the not so distant future.
Well, that's an interesting question. And I would say it's probably unwise to think of an ideal type of building that is suited to district energy. It's really proximity to a district energy utility that's more important. And enabling the expansion of existing district energy utilities is the way that this market is going to grow into wider adoption. Any type of building can be connected to a district energy network, and the advantages can be pretty dramatic. They include benefits to developers, owners, operators, and occupants. The developer obtains more square footage to sell or lease by minimizing the space reserved for heating and cooling equipment in the building or at the building site. The owners and operators of those buildings save on the cost of their energy because of the fuel flexibility that is enabled by the economy of scale of a large district energy utility, as well as savings on the maintenance and operational costs for their building. Instead of having large, complex combustion equipment on site and a skilled labor force needed to maintain it, that's eliminated, and they receive hot or chilled water, and they're getting their energy in a more usable form. Occupants can enjoy reliable, cost-effective comfort, partially insulating themselves from the market pricing of carbon fuels in districts that are successfully integrating this fuel flexibility topic. And everyone benefits from district energy solutions that can mitigate carbon footprint and move customers towards a net zero climate impact more effectively than any single building owner or consumer could do. In some really forward-thinking municipalities, there's regulatory support for district energy preparedness for both new real estate development and substantial renovation of existing building stock. The goal is to support expansion of these district energy networks through regulatory support during the building permitting process. So I find that to be really exciting because it eases the transition of a building if there's been some preparation up front. And these municipalities who are adopting that as part of their permitting process, I think, are deploying a really intelligent strategy.
Yeah, for sure. And I think we're going to see more of that forward thinking in the future as Audi in particular are planning for a lower carbon future in some of these places. But that said, I do know that we see some of these installations in more campus-like institutions, colleges, hospitals, military, right?
Yeah, that's right. I mean, the fundamental solutions don't change dependent on where the installation is. So, yes, college campuses, hospitals, military bases, they all have this concentration of buildings to be served within a border area, you might say. The equipment Danfoss provides is really well suited to all those markets. But we have found that college campuses represent strong current opportunities. And they tend to have dense building development within the defined border and are often already served by an aging standalone utility. Generally, they have greater freedom to make capital investment and operational decisions that can focus on the longer term. Many of those colleges also have thought leadership roles in the transition to green and net zero economies. So in those cases, there are additional and less tangible incentives for institutional change in the approach to heating and cooling buildings on campus. Those kind of interests often include consideration of low temperature district hot water heating networks, as well as district cooling systems that we've been chatting about here for 10 minutes or so.
Yeah, and it's also about resiliency, right? Because especially after, say, Superstorm Sandy and these types of events, these campus-like institutions, whether it's hospitals or military bases or college campuses, want to have some control and be able to come back online as soon as possible. And having one of these district systems, I think, gives them that sort of flexibility and resilience.
Yeah, as soon as there's a standalone solution, resiliency becomes a topic. So both in a positive way and also in a potentially negative way. So when I attend conferences around North America, resiliency is often a topic of discussion. But district energy can enable resiliency, so storm response. Your public grid of energy goes down, but you're able to supply energy for your own needs through your district system. There are also cases where in storm response, some of these smaller district utilities have actually been able to reconnect or redistribute some of their energy to their surrounding communities. And so they're providing a community service by being a little bit more resilient than the public utility.
Yeah, that's awesome. Like, when we talk about decentralized energy, I think district energy is an overlooked piece of that. But you're right. I think it does have a role to play there, particularly when you get into some of these places, college campuses in the Northeast, for example, that are relatively isolated, and they may be the only option if we have some widespread damage. So very cool stuff there. We've been talking district energy generally, and you, of course, are an expert in this topic, but Danfoss is not a district energy utility developer. We specialize in one specific piece, a very complex piece, but one specific piece of district energy. So why don't you tell us a little bit more about that?
Yeah, it's important that we talk about what we aren't at the same time when we talk about what we are. So we're really not a utility developer. Our role is more of an enabler. We're enabling the industry with engineered components and packaged equipment. The vast majority of that material is used to regulate the flow of heat transfer fluids in the district energy utilities distribution pipe network and to control the heat exchange between the district and the individual building or customer. So we're here to try to demystify heat transfer for customers and their consulting engineers. This ability comes to us from decades of experience designing and building packaged heat transfer equipment, something we commonly refer to in the industry as an energy transfer station.
And, I think that this is not really well understood technology. I had to give a presentation on this technology last year for a couple of colleges. And, this is usually a piece of equipment that's assembled piecemeal on site and by a contractor who may not necessarily understand district energy. They're used to doing some other stuff in HVAC and just assume that they can put one of these energy transfer stations together. But it's actually a lot more complex than that, right?
Well, to those of us who play with them every day, I guess we don't think of them as complex, but we are certainly trying to remove that complexity from our customers. So maybe I should talk a little bit about what an energy transfer station really is. I would describe it as it's a piece of engineered equipment. It has an integrated heat exchanger. That integrated heat exchanger isolates the district heating fluids, so the part that's at the central plant, from the energy transfer fluids that are circulating in the connected building. So those two fluids never mix. In addition to that primary heat exchanger, the equipment integrates pressure-independent control valves. So we are working to balance the distribution of the district fluids so that the first building, so the one nearest the plant, doesn't consume all the heat, extract almost no BTUs from the water, and pass less and less temperature to the next building. So we're working to control the distribution of the hot water in the network. We include the pumps for the secondary side, or the building side of the energy transfer is on this piece of equipment. There's also meters and an array of pressure and temperature sensors, and very importantly, an integrated controller. The purpose of the equipment is to regulate the temperature and flow of fluids on both sides of this heat exchanger to ensure both the building comfort and system efficiency from the district side. Does that help a little bit more?
Yeah, I mean, it does. It's kind of funny because that's exactly when we talk about pressure independent control valves within an individual building and a chiller and a boiler and pumps. It's pretty much the same system, except instead of the building being the end point, we're talking about, inside the building, talking about air handling unit and air coils up there. So it's really the same idea, just on a much larger scale.
Right. We're using pressure independent technology to balance two different systems. On one side, we're trying to balance the district utilities distribution of hot water. And then on the other side of the heat exchanger, we're trying to do the same thing with pressure independent control valves out to all the individual zones in a particular building. That's a great analogy, John.
Yeah. So we talked about the energy transfer systems. We've talked about the larger system, but now when we talk about getting into low temp hot water versus steam, what does low temp hot water enable you to do in terms of fuel source for district energy and mitigating greenhouse gas emissions and fossil fuels?
Well, when you think about it, these first generation systems that were generating steam, this question really drives at one of the unique values of modern district energy systems. Because as you evolve towards the distribution of lower temperature hot water, you enable the addition of lower grade sources of energy. If you no longer have to boil the water to make steam, or raise it to a temperature that's above its critical temperature so that it would flash into steam if it were not pressurized, the systems become quite a bit safer when you don't risk steam in the pipes. But more interesting to the efficiency question is, where is the energy going to come from now? When you no longer have to raise the temperature to above 212 degrees or close to 212 degrees, there are a lot of other sources of heat all around us that can start feeding the network. And for instance, we can use biomass, passive solar collection, geothermal sources. We can use the heat energy coming off of cogeneration facilities, even sewer heat recovery. And there's a very interesting project going on out in the Denver area right now where a relatively large tract of land is going to be redeveloped, and the entire source of energy on that plot will come from the sewer. Interesting there too, because the effluent from that sewer was flowing into a local stream where they were concerned about the rise in temperature having impact on species living in the water. So great benefit. Extract the heat from the sewer and save the water temperature in the river as well, and do good turns for species living there. But also surplus industrial process heat. It's really valuable to note that some of these sources are renewable, meaning they have low or near zero carbon impact. I like to think of this kind of like electric car technology. It's really unthinkable to imagine a modern electric car that does not incorporate regenerative braking. The brake energy doesn't get wasted. It's captured and reused. Similarly, cutting-edge district energy utilities are finding ways to capture, concentrate, distribute, and reuse increasingly smaller or lower temperature sources of heat energy. These technologies are really difficult and expensive to incorporate at individual properties, but the district energy utility can succeed. It's really about its greater scale.
And yeah, I think that's really what we're talking about, is scaling this stuff up and really capturing those efficiencies there. And, a lot of what you're just talking about, this idea of circular economy. And when we say that, we're mostly talking about manufactured parts and trying to figure out how to make those processes more circular. But, this is really circular economy when it comes to energy and waste heat and trying to figure out how to, use all parts of the buffalo, if you will. So really interesting stuff. Jeff, we covered a lot here and some high level stuff, getting some detail on specific components. But I think what is going to be really helpful is the next time we talk to Jeff, we'll be getting the specifics on an actual project in the Toronto metro area. And we can talk about how that project went and what it actually looked like. So I think this is really good preparation for that episode. So thanks again, Jeff. And that's it for this episode of the Engineering Exchange podcast.
You're welcome, John. Thanks for inviting me.
So that's it for another episode of the EnVisioneering Exchange. I'd like to thank my guest, Jeff Flannery, for joining us. And don't forget to subscribe to EnVisioneering Exchange on Apple Podcasts, Spotify, SoundCloud, or wherever you listen to your podcasts. And lastly, if you enjoyed this episode, please don't forget to rate, review, and share with your network. It really helps us out. Thanks for listening, and we'll talk to you next time.